The Taylor series is a concept covered in various subjects, yet it often remains underappreciated, even though it plays the role of a hero in numerous real-life applications. Taylor series is a way to approximate complicated functions with simpler ones. It's like trying to find a shortcut to describe a function more easily. For instance, consider approximating the cosine function, using a polynomial. You'll notice that by gradually including higher-order polynomial terms, your approximation becomes progressively closer to the actual cos function. The accuracy of the approximation is particularly noticeable near the point of reference, which is typically 0. Now, let's take another example, like the exponential function. To approximate e caret x at the point x equals 0, you start with a simple constant, which is 1. This is because we know that e caret x equals 1 at 0. To achieve a more precise approximation, you add additional terms one by one. With each added term, your approximation becomes closer to the true e caret x function. But why does the Taylor series work, and how do you determine which terms to include next? Let's dive into the underlying principles and methods. Let's break down the example of approximating the exponential function step by step. Our goal is to find a polynomial that can closely approximate the behavior of around a specific point. For instance, let's choose 0 as our reference point. In general, a polynomial can be expressed as follows: a plus b times x plus c times x squared plus d times x cubed plus e times x to the power 4, and so on, with various coefficients. We aim to determine these coefficients, and while it may initially appear complex, it's not as daunting as it seems. To start, we want our approximation to match the value of the function at the chosen point. We achieve this by simply substituting 0 into our function. When we do this for f, it equals e to the power 0, which is 1. Similarly, when we plug 0 into our polynomial, all terms vanish except the constant term, which gives us the coefficient a, and we find a equals 1. For the next coefficient, we differentiate both the function and the polynomial. This ensures that our approximation shares the same slope as the function. Consequently, we find b equals 1. Moving forward, we calculate the second derivative of both the function and the polynomial, ensuring that we maintain the same concavity. This leads us to determine that c equals 1/2. Continuing this process and computing higher degree derivatives allows us to obtain more coefficients, leading to a more accurate approximation as we include more terms. Up to this point, we've observed the effectiveness of our approach, where the polynomial approximation closely follows the function as we introduce higher-order terms into the polynomial. Now, it's time to establish a more general formula. We begin by calculating the first-order derivative for the polynomial, followed by the second order, then the third order, and so on. When we evaluate these derivatives at 0, we notice that for the polynomial, all terms with x vanish, leaving only c0. For the first derivative of the polynomial, c1 is the only non-zero term. And similarly for the second-order derivative, c2 is non-zero, and so on. Have you observed that the higher-order terms introduce factorial terms step by step? Therefore, it shouldn't be surprising to see factorials in our formula. So, we can express these coefficients as follows. c0 is equal to f. c1 equals the first derivative of f divided by 1 factorial. c2 equals the second derivative of f divided by 2 factorial. c3 equals the third derivative of f divided by 3 factorial. This lays the foundation for our Taylor series formula, which, at 0, is as shown. However, for any general point a, the formula transforms as illustrated in the animation and each x term becomes x minus a. I trust you found the video enjoyable. To stay tuned for more fascinating content, please continue following my channel. Don't forget to show your support by liking, sharing, and subscribing to my channel.